Okay, so now we'll move on to MODIS. So there are two satellite platforms that carry MODIS. One is called Terra, and one is called Aqua. They actually had a competition to come up with those two names. Each of them has a number of sensors on them. They both have MODIS. Terra has ASTER, which is a high spectral resolution thermal sensor, MISR, which is a multi-angle sensor, and then Ceres and MOPIT, which are both atmospheric sensors. So MODIS is carried on the Terra platform, which was launched in December 1999. It's then also carried on Aqua, which was launched in 2002 and has a similar suite of sensors. So you get almost two images per day for the Earth surface. So in Terra, you get a morning overpass. Aqua, you get an afternoon overpass. And so MODIS provides continuous global coverage every 1 or 2 days, mostly 2 days with the Aqua coverage, and collects data from 36 bands. As with Sentinel-2, those bands are not all at the same resolution though. There are 2 bands, bands 1 and 2, that have a resolution of 250 meters. 5 bands, bands 3 to 7, have a resolution of 500 meters, and the remaining bands have a resolution of 1,000 meters or 1 kilometer. And then the swath width for MODIS is 2,330 kilometers. So in order to get that fast revisit, you need to have a very wide swath. Give you a sense of what those bands are. Those first 2 high resolution bands at 250 meters, they are red and near infrared. So those are primarily used for vegetation, and then cloud boundaries and aerosol boundaries. The next 7 bands are used for, the next 5 bands are used for land properties. So that's when you're going to have blue, red, you're going to have near infrared, and then 2 mid infrareds. Those essentially are going to allow you in those first 7 bands to match thematic mapper bands. The next set of bands are associated with ocean characteristics. So you can see there are a number of blue bands there, 405 to 420 nanometers, 438 to 448 nanometers, 483 to 493. These are narrow bands that are used specifically for picking up things like phytoplankton density and biogeochemistry that's going on in near shore waters. The rest of the bands are all atmospheric, and so I don't have a background with them, but it's things like, as you can see, water vapor, surface and cloud temperatures are also done at 1 kilometer, atmospheric temperature, looking for the presence of cirrus clouds and water vapor in the atmospheric column, a couple of band in there for cloud properties, a band in there to detect ozone, more temperature bands, and then cloud top altitude, which as you can see is also done with thermal bands. Now the interesting thing about MODIS is it was part of a EOS or the EOS initiative, which was Earth Observing Science. And so the push then was to take remote sensing out of the hands of just remote sensing scientists and move it into a place where people from a variety of backgrounds were able to work with it. So as a consequence, the solution that the science team came up with was to have multiple products. Landsat traditionally you would get back a radiance value, so just an overall brightness. It would come as a digital number that you would then convert to radiance, and then you'd have to go through a separate set of analyses to get at a surface reflectance. With MODIS, you're provided with a surface reflectance as a data product. You're provided with land surface temperature, an estimate of emissivity, a land cover type, a series of vegetation indices, so you don't have to calculate them yourselves, thermal anomalies and fire. That's like a quick alarm product that tells you whether something has suddenly become hot. Leaf area index and fraction of photosynthetically active radiation, that's AVHRR. There are then model-based products like net photosynthesis, which again we'll talk about, net primary productivity, the evapotranspiration from the surface, the resistance to evapotranspiration, BRDF, bireflectance distance function, bireflectance distribution function, which kind of tries to correct for the different angles at which you're observing the surface of the Earth. A product that looks into just giving you whether or not there's been a vegetation conversion from one type to another, and then vegetation continuous fields that we'll discuss. If you look on this table, they're all produced at various spatial resolutions and temporal resolutions. So for instance, land surface temperature is produced daily at a 5 kilometer spatial resolution. And net primary productivity is produced yearly at a 1 kilometer spatial resolution. That green box there shouldn't be there. There is not a yearly net primary productivity produced daily, because that makes no sense. But then like surface reflectance is produced at an 8-day 500 meter spatial resolution, a daily 500 meter spatial resolution, an 8-day 250 meter resolution, and a daily 250 meter spatial resolution. Break up the various different land products from MODIS into 3 categories. One of them is the energy balance product suite. The second is the vegetation parameter suite. And the third is the land cover land use suite. So here we have an example for Southern Africa, where on the left we're looking at a surface reflectance that has not been corrected for aerosols. So you can think about this as a top of atmosphere reflectance. That is everything the sensor is seeing from the lens itself down to the land surface. And on the right, you've had aerosols corrected. And you can see it's a much clearer image. There's much better contrast. You're going to have a much better time trying to do, say, land surface classification on an image like this than you would if you had just used the image on the left, which is sort of a top of atmosphere correction. Now, I've talked about the fact that MODIS images come in various day lengths. That is, there's an 8-day product, there's a 32-day product, 16-day product. And in order to get those products, you're taking multiple images of the same area and stacking them up and asking what the best pixel, what's the clearest pixel that you can find from that stack of pixels. Okay, so You're saying over, say, 8 days, what's the best pixel that I got for a particular area? And the rule that's generally used is to find the pixel that has the maximum NDVI. And the reason is that the more aerosol and other scattering effects are involved in a particular pixel, the bigger the red reflectance is going to be. All right, so you think about Rayleigh scattering, it's going to affect the red reflectance much more than it's going to affect the near-infrared reflectance. And therefore, because that red reflectance is going to go up, the difference between the red reflectance and near-infrared reflectance is going to go down. And so, as a consequence, the NDVI that you get for that pixel will be lower. So you can use this maximum NDVI approach to take any number of daily images, or it could be, bi-monthly images, could be Landsat data, and get the best pixel for a time period. And that's tremendously useful because when you're looking over large areas, the chance that you're going to get good quality pixels in a single image is low. And so this is one way to get around that. And that's what it means when we talk about these 8-day composites. In addition to doing compositing, this image, for instance, is a 16-day composite. There's also the BRDF adjusted reflectance, so bireflectance distribution function. And when you've got a swath that's 2,300 kilometers or so, the sun angles at nadir are going to be very different than the sun angles that you're going to be seeing at the edges of the swath. That is, the illumination geometry of the sun to the surface up to the sensor is just going to be very different at the edges of the swath. And so one of the other things that the MODIS system does is it creates a BRDF adjusted reflectance. So it adjusts for those angular effects. And the nice thing about EOS is that, or MODIS, because it's part of the EOS system, is that BRDF adjusted reflectance is then used in subsequent calculations. So in some sense, all the products depend on the other products that are sort of more basic in the processing stream. Another automatic product is the image and snow map. We know that clouds and snow have very different spectral characteristics in the mid-infrared, and this product just takes advantage of that difference to classify out cloud and keep remaining the snow areas. And so here we have snow, we have land, and we have cloud. And then you can look at the change in the snow extent between various composite periods. Here between November 1st and 7th of the year 2000 and November 8th and 15th in 2000. And you can see that there's greater snowfall that's occurred between the 8th and the 15th than there was between November 1 and 7. Now, the depth of the snow is not something you know, but this does give you an idea in coverage, and Stephanie Camp of the ESS department has worked on just using this information about snow cover to actually generate estimates of runoff in streams. Land surface temperature product. So this is a daytime 1 kilometer land surface temperature. It's being shown at a 5 kilometer browse resolution, but so there's both the 8th day and a daily land surface temperature that's taken. And you can see it's pretty much hot where you'd expect it to be and cold where you'd expect it to be for this time of year. And of course, the empty areas are all cloudy areas. So those are your energy balance product suite parameters. Now about vegetation parameters. We know that either a simple ratio of NIR to red provides valuable vegetation index information, and the NDVI provides a level of improvement above that. On the image there to right, there's also displays then EVI, an enhanced vegetation index, that tries to bring in blue in order to correct for the amount of soil cover, particularly for dryland areas. And there's been some evidence that it works, but in fact, I think most people, for most purposes, continue to use NDVI because it's simpler. So here we have, hopefully in your presentation, information about greenness over the course of time, okay, with NDVI and EVI, and just showing you the greening up and browning down, particularly in the northern hemisphere, of vegetation as a function of time. And it turns out that this information is tremendously useful. There are the obvious things like looking at vegetation health and looking at crop productivity, but also individual vegetation types have individual or unique signatures. So for instance, if you're looking at broad evergreen forest versus deciduous forest, you can tell, just simple logic, that the evergreen forest is going to remain much more consistent than the deciduous forest. Mixed forest is going to act somewhat in between the two types. So that gives you an immediate idea of what kind of forest you might be looking at. Does it have high LAI, or high NDVI? Yes. Okay. Is it highly variable or isn't it? If it is highly variable, then it's probably deciduous. If it's not, then it's probably evergreen. The one caveat to that is that, in fact, conifer forests or evergreen forests, particularly in areas like Colorado where they don't have full cover, do show seasonal variability in greenness. And the reason is that you see the green background vegetation, the ground vegetation, greening up in the spring. And so there's some added greenness that these evergreen forests, whose canopies don't change very much in greenness, the canopy as a whole, when you include the ground surface, does in fact get greener and less green over time. And here's just another example of this, of greenness through the months of 2005, and showing in particular how the very dry areas of the Midwest and the north central states become green over the summer months and then back down to brown. Another data product that's generated is ice extent and temperature. So those studying the polar ice can get estimates of that without additional processing. Sea surface temperature, which is tremendously important, number one for fisheries. I think we've talked about this, looking for the signature of upwelling ocean waters that provide nutrients that support the food chain in places like off the coast of Peru. Also useful for weather forecasting. So the signature of an El Nino versus an El Nina year is the temperature of the water at the surface of the ocean in the equatorial region of the Pacific. Leaf area index and FPAR, which is the fractional photosynthetically active radiation absorbed. So leaf area index is basically the number of layers of leaves above a point on the Earth. So if you think about just sort of driving a spike through, from the top of some kind of vegetation down to the ground, it's how many times that spike is going to touch or intercept a leaf. So, low leaf area index biomes include things like, grasslands and scrub areas. High leaf area index areas include things like tropical forests, where you might get 12 layers of leaves above the ground surface at any one point. A similar product is FPAR. So PAR is photosynthetically active radiation. It's basically the blue and the red portion of the visible, and FPAR is the fraction that's being absorbed. So if you can see, a high level of FPAR is being absorbed. A high level of PAR is absorbed in forests globally, and in deserts, not so much. More complicated products that are created from MODIS. This is a global photosynthetic productivity map created by the University of Montana. And basically what it's saying is how many grams of carbon are being created within the leaves of plants per meter squared per day. Now that's not the total carbon dioxide uptake, because it's the gross primary productivity. Net primary productivity, in order to calculate that, you need to know how much is being respired, or either by the photosynthetic process itself, or in the evening when metabolic processes are going on. This is not, this is a much more complex product. It's based on net primary productivity, and specifically it's based on the models of net primary productivity. But I love the image, so I always show it. What you're seeing is a sensitivity analysis. So for any given point on the Earth, you can look at the model results for net primary productivity and say, what's the limiting factor? If areas in red, the limiting factor is water. So there's simply not enough water there to have high productivity. Areas that are blue, there's a temperature limitation. And so you see in the northern latitudes a lot of areas that are blue or cyan, because those are areas where you're not getting high enough temperatures in order to create more primary productivity. And then finally, areas that are green are radiation limited. That is, there's enough water and it's high enough temperature that you can create even more vegetation if you had more light. And that's what I find interesting, is that even in some of the temperate forests, but a lot of the tropical forests, they're light limited. That is, their photosynthetic mechanism is well structured enough that they could use even more light. And so cloudiness is the big limitation there. If there were fewer clouds, of course, if there were fewer clouds, you'd have greater productivity. If you had fewer clouds, you'd have less water. So then you'd have other limits to your productivity. But I've just always found that fascinating. So you've got the blue, teal areas or cyan areas that have high radiation limitations, like at the high latitudes, and temperature limitations at that same area. You have the red areas where you have water limitations, so the desert areas. It also shows just how dry it is where we are, kind of puts us into context that we're among the driest places on Earth. And then those green areas that are primarily radiation limited, and that's due to cloudiness. Finally, the land cover and land use suite of MODIS products. There is a 1 kilometer land cover product that's created every 90 days. So it uses that the view angle corrected, the BRDF corrected surface reflectance, and for all of the 7 land bands, that is the 250s and then 500 meters. It uses spatial texture from 250 meters. It used the vegetation index, snow cover, land surface temperature, and estimates of the bidirectional distribution function information itself in order to create a 17 class land classification. And then there are test sites for training all over the world. It's a very sophisticated algorithm. It uses multiple approaches to get at this final answer. And so this is from 2 16-day periods, just comparing MODIS, the more advanced, more recent sensor, with AVHRR land cover. And you can see quite a difference in being able to bring out a wider range of distinctions in, say, forest cover than you were able to with the earlier sensor. There's a change detection product, okay? So this is a change vector approach where you can immediately pick up whether or not an area has, for instance, as in this case, flooded during a time period just by knowing what changes in reflectance have occurred. It's another product, a tree cover map. There's a series of bands. You'll see bands or layers that are created that are the vegetation, continuous vegetation cover product, which gives you the percent tree cover, the percent soil, and percent herbaceous cover. So this is the percent tree cover map for the United States, and it's separating out the 2 kinds of green cover, woody and not woody. Then this is the continuous field product shown as RGB, where red is woody vegetation, green is herbaceous vegetation, and bare ground is blue. So you can see deserts and Greenland are blue, areas with high woody vegetation, forests are red, and then areas that are dominated by grasslands are green. The nice thing about this product is that particularly for places like Africa, it shows where there's a mix of herbaceous and woody vegetation. And of course, that's very important because those semi-arid areas support a big fraction of the Earth's population, and the shifting of woody to grassland vegetation is important there. There are then the MODIS fire products, and there are 3 fire products. There's a 8-day composite fire product. There's a summary fire data product that tells you about the composite is going to tell you if there was a fire there at any point. The summary is going to tell you something about um, how much fire there might have been during that time. And then finally, there's a daily fire product that's done at coarse resolution, 5 kilometers. This is a very important data product because the U.S. Forest Service uses this. Since it's MODIS, you can get a twice-day estimate of where there's fire. So you can get early detection and you can get extent of fire that you can use, and they do use in their daily fire planning.